So the big words on that one for IVT, intermediate value theorem.
Mr. Evans,
Yes?
if a function is like, because if it's not differentiable in the open interval but is on your closed interval, can you still like?
Wait, say it again.
If you like a function and like the absolute value function, but you only use like a part like away from like the corner, can you?
Sure, right? Yeah, that's why like you're talking about on an interval. So if you're talking about, let's use that absolute value of x function. If I'm talking about the interval, kind of like the quiz 0 to 2, I want to find a place where the average rate of change equals the instantaneous rate of change. Well, on the interval 0 to 2, is this a closed interval, continuous, and is it differentiable everywhere here? Is it differentiable on the open interval then? You know what I'm saying? Not including the 0? Yeah, so you can use it, and let's see if it guarantees it. Okay, so at 0, it's 0. At 2, we have a value of 2. y2 minus y1 over x2 minus x1. 2 minus 0 over 2 minus 0 is 1. The average rate of change of this function on this interval is 1. Is there a place where the instantaneous rate of change equals 1? Where?
The whole thing.
The whole thing, because it's a straight line. The secant line, is the tangent line, it's all of it. See that, you guys? But great question. Yeah, you can choose your interval, like wherever you want, but like what it is like, if you give me a closed interval, that's the only place I'm looking. For this function, I'm looking on this closed interval. Okay, is it differentiable here? And this one is yes.
So what about the open interval? Like when does that come into play?
Well, that just means like, I'll say this was differentiable on the open interval 0 to 2. Where this one is not differentiable on the open interval -1 to 1. So you just can't use mean value theorem. Did that answer your question? Yeah.
So does open interval mean that you're not counting the two endpoints?
You're not looking at the derivative at the endpoint.
Okay.
You're just going on the inside.
And then a closed interval would be looking at the derivative on the endpoints?
Yeah, but you're not going to be doing that. You're only going to be looking at it for continuous on a closed interval, meaning you need your endpoints. But then it's always going to be differentiable on the open interval. Everything except for the two endpoints. Like, is it a nice clean curve? Because you're just going to be coming, from the endpoint, you're just going to be kind of...
Because you can't see the limit from the other.
Yeah, you know what I'm saying? You can't check the derivative from the left. But like, if it was, if you're just off, then you can. You can check both sides. Okay? Good question. All right? All right, let's keep on going here. So was that fun so far? How are we feeling, Joanna? All right. Okay. So, did I ever tell my speeding story? I know I told it last year. Did I tell it this year? When I went into Missouri with the helicopter? I don't know if I told you guys. I told you guys last year. So here's a story. It's a true story. I'm driving in college down to Memphis. And I just pull in, you cross the Mississippi River. We go right into Missouri. And I'm driving my big Aerostar. I got the big blue minivan because I'm cool. I'm in college and I drive a minivan, which is awesome. It actually is awesome. I don't know why you're judging, Eric. That's actually, it's kind of random. All right, so right? I mean, it's so cool. Like everyone's like, "Hey, was Walk 417 at the Jewel today?" I'm like, "Yeah." Anyway, it was a cool van. Anyway, so I'm driving, I'm cruising, and I got something in my eye, and I'm like, "What is this?" And then I look, and there's literally a cop that I almost hit. He's standing in the middle of the road. Literally. And he had to jump out of the way. I'm like, what was that? He was telling me to stop. But I was like, by then I noticed him. I was like, whoa. And so they get a squad car, they come and pull me over. And they're like, you were speeding. So the speed limit was 65. I was just going 66, obviously, just because I wasn't paying attention for that second. So I was just going a little over, but they pulled me over. But I'm like, you were going this speed. And I'm like, what are you talking? You're just standing in the middle of the street. Like, what are you talking about? I was speeding. What they did was, they have a helicopter, and they painted 2 white strips on the street, and they were just timing people. So they figured out the total distance you travel. It was like a quarter mile, so between the strips, and they would just time people one at a time. And they took that total distance divided by the total time it took you, and then they found your average velocity over that interval. And what they said was, if you averaged more than the speed limit, then there had to have been one time that you were going that fast. Does that make sense? That literally happened. I was like, foiled by math again. But that's a true story. And so this is kind of the same thing. That is mean value theory. You know, that they used it against us in the court of law. I didn't go, I just paid my tea. Some people contested it though. They got a whole bunch of those. So here's an example. So here's one. If a car is accelerating, so accelerating, let's say it starts at 0, and it just go. You know, we're accelerating, we're speeding up, and it takes 60 seconds to go this 1 mile, and you've been speeding up the whole time. Its average velocity over the interval would be, okay, so you traveled the 1 mile in 60 seconds. So then, you know, what I did was I divided 1 divided by 60, which is 0.0167 miles per second, and then I just converted that to hours, and you get 60 miles per hour. So what I did was I averaged 60 miles per hour. Okay, that was my average over the interval. What the theorem says is that at some point between 0 and 60 seconds, that speedometer had to have passed or said 60 miles per hour. Does that make sense? Because if you're accelerating, you start lower and then you wind up going higher and you average 60. You know what I'm saying? Like you're speeding up. That means that at 1 second, at some point, you had to have crossed the 60. The speedometer went 60, like Chip. You know, he's like, you're at 60, Michael. No? Is that right? Does that make sense? David? Okay. So that's what it says. At some point, the average rate of change is equal to the instantaneous rate of change. It could be more, but it's at least 1. Okay? So here's some stuff with increasing and decreasing functions. Okay? And we've been talking about this a little bit, but here's some nice little notation, and they threw it in the section. Let f be a function defined on an interval, and let x1 and x2 be any 2 points on the interval. Then, if x1 is less than x2, what that means is x1 is left of x2, or it looks like this. There's x1, there's x2. x1 is less than x2 if you're increasing. Then the function value at x1 has to be less than the function value at x2. Right? This value is less than this, then this value is less than this. If you're increasing, because as you go right, you're going up. Okay? And it's just the flip of that for decreasing. As you go right, you go down. So this sign is just going to be flipped. That means the f of x1 is actually going to be bigger than the f of x2. So that's what that notation means. Excuse me. Let f be a continuous function on the closed interval and differentiable on the open interval. If the derivative is positive, again, a way to write that is f prime of x greater than 0. If the derivative is positive at each point on the open interval, then f is increasing on that interval. If the derivative is negative at each point on that interval, then f decreases on that interval. There's somewhere in the notes, did you see I spelled original right? Did I get to it yet? Did you notice it or no? We'll get to it, I think. This allows us to figure out when a function is increasing or decreasing and stated using intervals without looking at the graph. And again, this is what we did, or what people did for many, many years before these wonderful graphing calculators. They did all this by hand. So here, let's look at this example right here. X squared minus x minus 12.